Let's get it. All right, so we already read this. Now we're just gonna get some practice. Okay, so locate the bifurcation values and then draw the phase lines for values of the parameters slightly smaller than, slightly larger than, and at the bifurcation values. All right, cool. So we're just going to hammer these because surely this will be on my quiz. Okay, so dy dt is equal to y squared plus a. So our fixed points are going to be y squared plus a is equal to 0. So y squared is equal to minus a, y squared, or y is equal to plus or minus square root of minus a. So let's say if a is equal to 0, then we have one equilibria. If a is less than 0, 2, and then else 0. So, okay, cool. So the bifurcation value is a is equal to 0 because y squared plus 0, then we're going to have 1 point, and it's going to be a node actually. So okay, so let's do 3 phase lines. So these are the 3 phase lines, and this is going to be, so if we were to like a, so this is going to be a is less than 0, maybe like a is equal to minus 1. Then we're going to get square root of 1, which is 1. We're going to get 2 fixed points at plus or minus 1. So this is going to be 1 and minus 1. So now if we take the second derivative, if we take y squared minus 1 yeah, well, we can see we can factor it into y plus 1, y minus 1. But the main thing is that if we take this f prime of y, we're going to get 2y. And 2y, 2 times minus 1 is less than 0. So that means that this is going to be a sink. Therefore, sink. So at a is equal to minus 1, we have a equilibria at minus 1, which is going to be a sink. And we could just double check that by testing. Let's do minus 2. So we're going to get 4 plus minus 1 is equal to 3, which is greater than 0. So dy dt is greater than 0 at a equals to minus 1, y equal to minus 2. All right. The next one we want to just double check is whether or not 1 is a source. And so we're going to get 2 times 1 minus 1 is greater than 0, so source. And we can double check that. Let's say we have 4 minus 1 is greater than 0, which is y squared minus 1. Okay, great. Now let's do a is equal to 0. We're going to get just 1 point here. And we're going to get, so y squared is equal to 0 has one solution at 0. And y squared is going to be positive for any value of y. So therefore we have a node pointing upward. So this is a is equal to 0. Now a is greater than 0 for a equal to 1. We're going to have y squared plus 1 is equal to 0. And this is going to have no solutions. But it is always going to be positive. So there we go. So now if we were to just do if we were to actually make a bifurcation plot, we should get like something like this. So we have arrows like this, arrows like this. We have okay, great. So this is going to be the A, Y. All right, so number 2. So now we're on to this one. It's getting very mechanical. It's getting pretty easy. All right, so for the second one, we have dy dt is equal to y squared plus 3y plus a. So the first thing we're going to do is we're going to set it equal to 0. So y squared plus 3y plus a is equal to 0. So now, this is one of those ones where, in all honesty, the easiest thing that we can do is just use the quadratic formula. So we're going to have, so y is equal to minus b, which is 3. So minus 3 plus or minus the square root of 9 minus 4 times a, which is 1, times c, which is a. So minus 4a over 2a, which is going to be over 2. So we're going to have so the main idea is now we look at the discriminant. I think that's what it's called, the discriminant, the thing that's under the square root. Because if that is negative, then there's going to be no solutions. So that's sort of how we're going to find the bifurcation value. All right. So 9 minus 4a equal to 0. So what we're going to do is a is equal to 9 over 4. So that is going to be the bifurcation value. Almost, I mean, it is. It is. So if a equals that, then y's fixed point is going to be equal to minus 3 plus or minus 0 over 2, which is equal to minus 3 over 2. So now if we just plug in for that, we get 9/4 plus 3 times minus 3/2 plus 9 over 4. So we're going to get okay, and then I verified that that's actually a 0. So for the middle phase line, we're going to say A equal to 9 over 4. And then we're going to have a single dot at minus 3/2. So this is going to be the 0. Now, if we were to take the derivative, so now we want the linearization test. So for the linearization test, we're going to get 2y plus 3 is equal to f a prime of y. So we're going to get minus 3 plus 3 is equal to 0. So actually, it's not going to tell us anything because it's 0. So what we can do is we can just evaluate dy dt at like minus 2, for instance. So we're going to get 4 minus 6 plus 9 over 4. That's positive. All right, and then let's do y equals 0, and that's positive as well. So that means that we have a node here. And actually, what we're going to have is, again, we're going to have the case where if a is less than 0, then we have 2 solutions. And if it's greater than 0, we have no solutions. Or, sorry, greater than... All right, so let's draw another line here. This is going to be a is less than 9 over 4. So let's just pick a is equal to 0. So if a is 0, then we're going to get y times y plus 3, which has 2 roots, y equals 0 and minus 3. Now what I want to do actually is let's go to Desmos. And let's, if we did y is equal to minus 3/2 plus, or let's do that. Oh, wow. Right, when a is 0, but so that's the full thing. Oh, but okay. But we're talking about so this is the actual bifurcation plot itself. Because 2.25, is that 9? I think that's 9 over 4. It's 2.25. So this is the 9 over 4 that we were talking about. So then, yeah, 0 minus 3. That's... Okay, good. Okay, the last one is going to be the case where... So wait, first we need to actually do the linearization test here. So we're going to have minus 6 plus 3, which is less than 0. So this is actually going to be Oh, no, it's less than 0, so it's going to be a sinc. So sinc and top one's going to be a source. So okay, great. So 3 is done. Or 2 is done. Now we are going to do y squared minus ay plus 1. Okay, so again, I mean, that's the interesting thing about these books that have a lot more like symbolic manipulation and calculation and just handwriting in them, is like they actually lead you to believe that you can do more than you can, because you relying on this quadratic formula thing is like it just doesn't scale to higher degree polynomials. Anyways, so what we're gonna do is the quadratic formula again. So we're gonna do y is equal to a plus or, so let me just highlight. We're doing this one now. So b is gonna be oh, I'm actually, let me think. A is just a. So we're gonna have minus a plus or minus the square root of a squared minus 4 over 2. I'll be right back. All right. So again, we're gonna just look at the discriminant here. So we have, and wait, I actually want to remember, what do I need to review? I need to review 1.6 because I got hella cooked by the integration stuff. All right. How's my volume? A little bit low? How about that? Test, test, Okay. So for a squared equals 4, a is equal to plus or minus 2. Oh, wait, this one's interesting. So okay, so if a equals, wait, so what does that mean? That means that we have two values of a. We have two values for a which give a single solution to y. Okay, so if a equals 2, then we have minus 2 plus or minus 0 over 2, which is equal to minus 1. Similarly, if a equals minus 2, we get 2 plus 0 over 2 is equal to 1. So wait, can we just... I really like plotting it. So if we just copy this, we make this minus x Oh yeah, it's like weird. It's like this weird, I don't know, hyperbolic thing. I don't know what the hell you call this. I review my trig to remember. I think it is called hyperbolic, but I don't remember. Oh, this one's so cool. Okay, so in this instance, yeah, so we're gonna have this minus 2 and this positive 2. That's what I found. Okay, cool. Okay, so now I'm going to get f sub a prime of y, which is equal to 2y minus a. So we need to actually do... So the bifurcation value is a is equal to plus or minus 2. So we have two bifurcations in the system. All right, so the phase lines are going to be... So let's just do... This is going to be a is equal to minus 3. So we're going to have 9 minus 4. So we're going to have 3 plus or minus... 3 plus or minus square root of 5 over 2. So I don't know what that is, but, well, we could just do this. At 3... All right, who cares? It's just, we're going to have 2 of these. Actually, we do kind of want a nice value, right? Because if we do, we're going to get... So this is a is equal to minus 3. So we're going to get So these are the two values. So the first value is 3 plus square root of 5 over 2. And if we subtract, so we multiply that by 2, and we subtract minus 3. So we're going to get a positive number. So we're going to get a positive number. So this is actually a source. Let me just double check that. So we have y squared minus, or plus 3y plus 1. Um, and if y equals, what did I say, minus 3? So we're going to get 9 minus 9 plus 1 is greater than 0. So the slope, wait, so this is, oh wait, hold on. I just computed, wait, oh, I just did the wrong thing, that's why. Okay, so what I want to do now is just, I just want to, do this. So f of y, f of x is equal to, and it's going to be, yeah, x squared plus 3x plus 1. And then we're going to call f of, and this is going to be 3 plus square root 5 over 2. And then I want this one. Wait. They can't. I think I did something wrong because they can't both be. I mean, we showed in the last video that they can both be, but I just don't think they are in this case. They, and by both be, I mean both be nodes, right? Because, or not nodes, but they both be sources. So if we were to just plot x squared plus 3x plus 1, see, this is going to be a sink because it's going from positive to negative, which means that the f prime should be negative here, but I did something wrong. How did I do something so wrong? Oh wait, because we're evaluating f, not f prime. Wait. Oh. I'm a silly goose. Okay, so what are we doing here? Yeah, these problems are actually harder than I thought. So what we need to do is, let's just recap. So what did we do so far? What we did so far is we used the quadratic formula to find the values of A that cause Y to have a single solution. And in doing that, we found that actually there are two values of A that do that. Then we plotted those two different solutions being -2 and +2. Now what we're trying to do is I guess we want to draw let's just start with, we draw the phase lines for the bifurcation values. So in that instance, what we're going to do is A is going to be -2. Then we're going to plot a phase line for A is equal to -2. And what we're going to do is we're going to have a single point here. And the way that we find this point is it's going to be the value of Y for when we do -2. So A, we're going to get a 1. So this is going to be Y is equal to 1, A is equal to -2. So that's going to be this point. So we're now doing the phase line for this point. And what we want to do is we want to do our linearization, which we should expect to give 0. So we get 2. Wait, should we expect to get 0? Hold on, let me think about this. So what are we talking about? We're talking about the linearization at A is equal to -2. So we're going to get 2Y plus 4. So, but that's what's weird, is that shouldn't this be a node? This should be a node because it only has one value. But here we're saying that it looks like, can you have, let's see, what is an example of a differential equation that has a single phase line that's a sink? Or a source. Can you have that? Is it possible? Minus x. Let me think about that. So that means that f prime, so let's say x dot equals minus x. Then then f prime Wait, but that has no parameter in it, right? Oh, I guess it doesn't need a parameter. I mean, we could do actually our simple exponential growth model. So x dot equals ax, and then we just set a is equal to -1 as a bifurcation point. So if we do ax equals 0, actually that's a good problem. Oh, they do it like this. Oh, so it's not ax, it's a minus x. All right, but let's do the phase line. So at yeah, okay, all right, that makes sense. So you can have that, but is that what this looks like? Oh, well, all right. So let's remember where we're at. A is equal to -2, y is equal to 1. So if we do 1 plus 2 plus 1, and then if we do all right, so now we're going to do a is equal to 2 and y is equal to -1. So wait, no, we definitely did something wrong. No, we definitely did something wrong because these are supposed to be values for which dy dt is 0. Because all these are supposed to describe the fixed points, but I just computed dy dt of a equals -1 because we're going to have 1 squared. All right, let's try the other one. If we try the other one, it's going to be 1 Oh, wait. It's going to be 1 minus 1 squared minus 2 times minus 1. So we're going to get 1 plus 2 plus 1 is equal to 4. Yeah, okay. I definitely botched something. Okay, we're going to start 3 over. So if all right, so we have Jesus. Y squared minus ax plus 1. Or y, Jesus. Okay, so we get okay, so let's try this. So we're going to get, let's choose a equals minus 2. So we're going to get y is equal to 2. Let's say 1/2 times 2. Dude, I'm flipping a minus sign somewhere, and it's driving me absolutely crazy. See, that's what's weird to me. I knew that that was what it was going to be, is that B is actually minus A. That's why, because, okay, all right, that's why. Okay, so really what you have to do is you have to make it a plus. All right, so we're going to start over. So we have A, so A is equal to 1, B is equal to minus A. That's so confusing, but that's fine. And the C is equal to 1. Okay, so we're going to get minus B. So we're going to get see, that is my fatal flaw. Okay, so we're going to get Y is equal to A plus or minus B squared, which is going to be minus A squared, which is equal to A squared minus 4 over 2. So we're going to get Nah, I'm chill, bro. I'm chill. Now that we figured it out. So it's going to be A plus or minus A squared minus 4. So we still have A is equal to plus or minus 2. So let's just pick minus 2. So we're going to get y is equal to minus 2 plus 0 over 2 is equal to minus 1. So we have actually a equal to minus 2, y equal to minus 1. So it's flipped. So I flipped it. So what this needs to be is like that. Okay, so now if we plug this in for the original dy dt, we're going to get 1 minus 2 times minus 1 is equal to 1 minus 2 plus 1 equal to 0. Okay, great. All right, now we're back on track here. So what we want to do now is we have f prime of y is equal to 2y minus a. And so if we plug in, we're going to get minus 2 minus minus 2, which is equal to minus 2 plus 2 is equal to 0. So yeah, okay, thank God. So these are nodes. These are nodes. So we need to do more testing to figure out which direction they go. So what we're going to do is we're going to plug in a equals 0 because basically when you carve out space, this whole space is going to have the same sign. Which is crazy to me because you actually really, yeah. I mean, the equilibria of differential equations are by far the most important points. I mean, they just totally characterize the system. So anyways, so we're going to get, so for a equals 0, all we have to do is evaluate. So we're going to get y squared plus 1 equal to 0. They're not 0. We should just be able to evaluate y equal to 0, then we get 1. So it should be an arrow pointing upwards. So the slopes along all of these should be pointing upwards. So if we were to draw, let's say this is going to be, all right, so what we should get is, okay, so what we want to test now is y prime, which is 2y minus a, for a is equal to minus 3, and y is equal to the solution at that point, which is kind of annoying because so I should be able to just do this, right? Oh wait, isn't there a fast? Can't I do slash dot a goes to -3. Can't I just do this? Okay, wait, but what we want to do is then use that as the input. That didn't do anything. So what we want to do is, so we have these solutions. We want to I think this is a map, right? No. Let me just learn something. I think I can just do this. I can do 2x minus and then I put this in parentheses maybe. Is that actually true though? So we have, so wait, so first off, let's just get this. So we have y is equal to -3 plus or minus square root of 5 over 2. So now we want to do, so we're going to get -3 plus or minus square root of, or let's just do one of them. -3 plus square root of 5 minus -3. So we get square root of 5. So the sign is, oh, wait, hold on. What did I do wrong here? No, because I did the plus. Yeah, the plus has a positive sign. So this corresponds to the more negative solution. So that's going to be that one. Okay, so I think I did it. I didn't evaluate all the phase lines because there was a lot. There was a lot of them. This one was a really good problem. But it goes to show that there can be, this is why doing the exercises is important, because you actually get a look at the diversity of possible things that could happen. You know, you read the textbook and you see a couple of examples and you're like, okay, that's kind of what happens. But then there's all sorts of other stuff that could happen that you don't see. Like this one with the 2 bifurcation values. Crazy, man. That's really crazy. All right, let's do number 4. Okay, number 4 is dy dt is equal to y cubed plus ay squared. So this is, as we said, it's a 0. We can factor out y squared y plus a. So we're going to get, okay, so just immediately I see that there's a y of multiplicity 2. And then we have a y plus a, which has, so our zeros are going to be y is equal to 0 minus a. So I believe the bifurcation value is again. Wait, can we actually read what this is? Yeah. Wait a minute. We never did that? Wait, that's a sync? Okay, so y equals minus 1. A equals minus 2. Minus 2. Oh, wait, no, what? The equilibrium is non-hyperbolic. Why are they saying crazy words to me? So the branches collide. Whoa, I don't. What? Saddle node. I don't know what saddle node means, but okay. I'm pretty sure. I'm pretty sure. We did that one right. Okay, so this one, the bifurcation value is going to be a is equal to 0. So what do we need to do? So first off, f prime for our linearization of y is going to be 3y squared plus 2ay. This is going to be y times 3y plus 2a. So solving for a, we could do this. We could do 3y squared plus 2ay is equal to 0. Subtract, so then we get 2ay is equal to minus 3y squared. We divide by y, we get 2a is equal to minus 3y. So a is equal to, or actually, do we want to solve for, we want to solve for y. So y is equal to minus 2/3 a. So what does that give us? That gives us an easy formula for determining, for a given value of a, whether or not, no, I don't know, whether or not it's a sink or a source. I'm not quite sure. So our first thing is that if a is 0, so let's just get the phase line for a is 0. So a equal to 0, we're going to have one equilibrium point at y equals 0. Now what we want to do is compute for like value slightly less than and greater than the derivative, or the, the change, so that we know what the sign is, because the linearization is giving us 0, which doesn't tell us whether it's attracting or repelling. So we can't use the linearization test for a equal to 0, y equal to 0. So let's just try y equals to 1. We're going to get positive. So, and then y equals minus 1. Minus 1 cubed equals minus 1. So we're going to get, so this is a, so this is actually a source. And you can see that if you just, let's remove all of these. If you plot x cubed, or x cubed, this is a source, because the derivative is negative here, so it's going to go away from it, and the derivative is positive here, so it can go towards it. Okay, so y equal to 0 is a, so let's do, okay, so let's just say if a is equal to minus, but wait, what am I trying to do here? I'm trying to find, a formula that gives me, that characterizes the, okay, well, let's just evaluate a few points instead of trying to find the family. So if, let's just say a equals minus 1, or let's do a equals 1, then we're going to have, for that, we're going to have, wait a minute. Yeah, wait, okay, this graph might look sick. All right, we'll find out. So if a equals 1, then we have y squared plus times y plus 1. So if y equals minus 1 or 0, so we're going to have minus 1 and 0 is going to stay a solution. So this is y equal to 0, and this is equal to y is minus 1. So we can evaluate our linearization. So we have, so the y equals 0 case is still inconclusive, but the y equals minus 1 case, we're going to get 3 times minus 1 squared, which is 1, plus 2 times 1 times minus 1, which is going to be 3 minus 2 is greater than 0. So that means that this is going to be repelling. And now what we need to do is we need to evaluate dy dt for y equal to 1, which is positive, because the linearization failed. So we're going to get, for y equal to 1, we're going to get 1 cubed plus 1 times 1 squared, which is equal to 2. So that means the slope is positive, so it's going to be repelling. So we have a source and a node. And now what I want to do is I want to evaluate for the phase line, a third phase line, for a is equal to minus 1. So if a equals minus 1, then we have y squared times 1 times y minus 1 as the differential equation. And in that case, we're going to have a solution at y equals 1 and actually it is correct to say that that's a solution because it is a solution. It's the equilibrium solution. Dude, bifurcations are so cool. This is my favorite section of the whole thing. And y equals 0. So now we can do our linearization again. So we have, let's do the one that we know is going to work. We're going to do 3 times 1 squared plus 2 times minus 1 times 1. So we're going to get 3 minus 2. So this is going to be a... Alright, so if we were to plot this... So for a equal minus 1, I think it actually might be a line. And this is a source. Okay. I'll make some plots and we'll show what that looks like. Okay. So yeah, so I think that what this bifurcation plot is would look like is you're gonna have a y is equal to x. Actually, wait, did I do this wrong? Oh yeah, I flipped it. You're gonna have y equals to minus x, and then you're gonna have y equal to 0. So here at this point where a is equal to 0, the differential equation collapses to just y cubed, and we get a source. So the arrow is pointing up here, pointing down here, and then so it's going to be pointing down for this whole part below this line and below this line. Now above this line, the arrow is pointing up. So now the only question is, what's in between? And it turns out, I think it's down here and up here. Okay, next problem. So we have y squared minus a, y squared minus 4. Okay, so we are... Wow. So the set of solutions is going to be plus or minus the square root of a and plus or minus square root of 4. So plus or minus square root of a, 2 and minus 2. Whoa. Dang, this one's weird. It's so funny how each one of these is actually really cool. You think it's like, all right, it's going to get boring at some point, but it doesn't actually get boring. So how are we going to tackle this? What is the freaking way we do this? You know, before it was easy when it's a quadratic, because you could just find the collapse. But okay, so anyways, I mean, we have pretty good intuition that a equal to 0 is going to be important, because that's when because when a is equal to 0, 2 fixed points collapse into one fixed point, because square root of 0 is just 0. So you're not going to have the branches collide. The branches collide, basically. So the bif value is a is equal to 0. So that's going to be the bifurcation value, but what we need to know is what this space looks like. So first off, I mean, this is always just good to do, I feel like. Is this cheating? I don't know. But y squared, let's say minus 1, y squared minus 4. Oh wait, Desmos wants it as X. Okay, yeah. Oh, I was okay. That's so good. That's great because I was actually. Oh, awesome. So yeah. Oh, wow. This is going to be one of my favorites for sure because not only do you get this. Was it in the book that we got that crazy looking curve? Yeah, this one. I want to do a problem like this one because this is crazy. Because you have these. I mean, this one line divides the whole space, but you have these weird pockets. Because, like, out here, they could just go to infinity really fast, but here they're going to approach something. So they're, like, quite different. Like, being here or being here is, like, really different. Even though the direction you're going is the same, you're going to be going at a way different speed. Likely. Because this thing has to hit infinity. This thing out here, because there's nothing to stop it. So it's just going to keep going and going. Okay, so we're doing this one. So the point is, okay, so let's set a equal to 0. So at 0, we have 3. Yeah, but what's nuts about this is that there's another bifurcation in here that so wait, if we recognize y squared minus a, or minus 4 squared only has 2 solutions. And if I keep going, so wait, but it never, no matter what, so it goes from minus 2, goes from, geez, I hate this slider thing. It goes from minus 2 to, so wait, it goes minus 2 to, or wait, sorry, not minus 2, 2, so less than 0, and then at 0 it becomes 3, so this is at a is less than 0, then at a equal to 0 we get 3, then a greater than 0, but we get 4. But then there's a crazy, like, double bifurcation that happens at a equal to 4. Then at a equal to 4, we get a 4 to 2 collapse. And then at a greater than 4, we go back to 4. Whoa. Now that is crazy. What the heck? So it goes 2 to 3 to 4 to 2 to 4. What the freak, dude? Okay, so 0 and 4 are the bifurcation. But the thing that is bothering me is I don't know how to recognize that 4. I mean, I guess I do, but it's like to recognize that A is equal to 4 is also a bifurcation value is way harder than the 0 case, I feel like. So, okay, so wait, let's just if I do isn't there an operator? What am I trying to do? I'm trying to what am I trying to do? I'm trying to do x squared minus a times x squared minus 4 expand. And then I want like a d, but I want like an operator form of d, like a one argument d. Oh wait, can I do this? No, that's see that because this doesn't do what I want. Well, why is this weird? Oh yeah. Those are always so crazy to me. The hash and because hash and what is that? What's the full form of that? Because you do d hash x and I want to do a full form of that. I probably need to hold it. I probably need to hold. And then how do I compose functions? Like if I do this, hold at star. Is that gonna work? I think it's because of I think it's the precedence that's messing me up. I think I need to do this. No, let's just delete this. Yeah, that's so cool. I mean, that's the thing, is that they just have so much cool syntax. It's like so hard to remember, but dang, is it powerful. Oh, wait. Okay, so there we go. So there's our f prime. So let's just get our f prime. This can be equal to minus 8x minus 2ax plus 4x cubed. Dude, this exercise is kind of blowing my mind. I'm actually I'm not stumped, but I just know it's going to be so much work. Okay, so anyways, let's just think about it more broadly, not considering that we have more work to do than the other ones. So we know the bifurcation values. The bifurcation values are a is equal to 0 and a is equal to 4. Okay, so let's just start off with a is equal to minus 1. So we're going to go over here. We're going to make a minus 1. Okay. So we're going to have a plus 2 and a minus 2. Y is equal to 2. Y is equal to minus 2. And by the linearization, let's just say this is we should be able to do FP slash dot X goes to, oh wait, no. What am I trying to do? Oh. Okay, so the negative is going to be a sink, and the positive is a source. Wait, what is going on? At y is equal to 0, we have 3 equilibria. Now, we can evaluate... Whoa. Okay, so they're both negative. And we still have that the lower one is a sink, and this one's a source. Now, A is equal to 2, let's say. Or let's do 1. Okay, so for A equal to 1, oh, you know what it might be? The bifurcation plot might look like this. Hold on. So it's going to be like a leftward parabola where like so first we're going to have y is equal to 2, y is equal to 4, or minus 2. Okay, then we're going to have like x squared equal to y. No. Like that. Except they can't cross. So it's more like, how do we make it? How do we make it? That's what I think this graph looks like. I think. But we're not done, so we have to wait and see. It could be. It could be something like that. The way it approaches can be different, though. So it doesn't just have to approach it in a. Wait, let's finish my graph and then we'll ask ChatGPT for its graph. But I don't know if it's, tan H or what. I don't know. But it does seem like this one's really cool because it shows how you can combine them, right? Because if we were to just consider y squared equals y squared minus alpha as the differential equation, the bifurcation would be 0. Wait, actually though, I don't know. Okay, so so we need to do this. We need to do f prime where a goes to 1 and x goes to -2, -1, 1, -2. Okay, so we get a sink, a source, a sink, and a source. Okay, now this is going to be a is equal to 4. So at a is equal to 4, right, those solutions become the same thing. So we're only going to get y equal to 2 and y equal to -2. So now we're going to do this. A is equal to 4. X is equal to -2. Oh, wait. Okay, yeah, that's fine. Oh my God, that's crazy. That's what I was saying. No, that's what I was saying. Is it's possible to construct. So wait, let's go back to. Let's go back to this graph. So here, it's positive on this side and it's positive on this side. So therefore, that's a node. And then this one also has the same thing. So that's also a node. Wait, this is where it's getting really trippy for me, because when we were talking about this, I implicitly assumed that this can't cross, but they can cross. It's okay for them to cross. We've seen that in the other examples. So in actuality, I think that this is this. Okay, cool. So this is the bifurcation plot. This is the whole thing. And it can cross. Wow. That's insane. Trajectories can't cross, but our bifurcation plot solutions can. Dang. Okay, so now let's pick, like, what's a good number? Is there going to be any good number? 9? 9 will be good. Let's do that. So we're going to have like -3, 3, 2, -2. And okay, so now what we want to do is let's do this. FP, A goes to 9, X goes to -3, -2, 2, 3. So we're going to get a sink, a source, a sink, and a source. So it's plus all up here. It's minus here. It's plus here. So if we were to draw this full thing, we're going to get 2 lines, and then we're going to get this. So it's minus here. It's minus here. It's plus in here. It's plus out here. It's plus below. And it's minus here. That's so cool. Wow, that is the best one yet. Dude, this one's gonna probably blow my mind. I hate absolute values though. Absolute values are too confusing for me. But dang, this one, dude, this one's sweet. Wait, let me see if the camera will show my plot.
That's what it looks like.
Ooh, we haven't done one with trig or exponentials. That's gonna be cool. I might need to end and pick this up in like 30 minutes because it's gonna get real noisy. So I might just go on a walk and wait. I'll be right back. Okay. Okay, yeah. I'm gonna pick this up in a minute.